Hi everyone, greetings from Saudi Arabia. Hope everyone is doing fine. I'm just going to go a little bit into the DNA metabarcoding like workflow with dada2 and R, which is a tool that is widely used for sequence analysis. And I'm just going to give some general introduction, and then I have prepared a script which I'm going to run live, so you can see like all the output and all the steps. And yeah, so. So what is the advantage of using dada2 and R? And first of all, like R and R studios are widely used in the scientific community. You probably all have worked with it, and so there is a lot of support and forums and tutorials on the World Wide Web whenever you have issues. So this is actually pretty good. Then dada2 is now a tool that is widely used for metabarcoding, especially of course for microbial metabarcoding, but also increasingly for animals using the CO1 marker. And nowadays, most of the manuscript papers add their scripts to the supplementary material or on their GitHub pages or whatever. So it is becoming easier to learn from those papers and to reproduce the workflows and to take like bits from here and there, basically. Also, what is very important for me as a user is that dada2 is a tool that is being used a lot, and where the documentation and the support, especially via the GitHub issues page, is really, really great. Sometimes I'm also using some other tools, some other packages for whatever someone has developed then, just like put up a GitHub page and then never really replies to issues anymore on the GitHub page. So this is really different for dada2. Usually replies are come within like a few days, and so this is really great with dada2. Yeah, so for me, like I'm not a bioinformatician, like I'm also just started my master's studies, so like I am also pretty new to all of this. But even for me, it is kind of simple, like understandable what is going on in the workflow and how this works. So this is important for me, and it's also important that I can run this in a decent condition on my personal computer, because some of us don't have access to HPC, so high performance computers, or even if we do have it, we don't know how to access it or whatever. So this is actually pretty cool. I do have a decent computer, like a good amount of RAM is needed, of course, but yeah, it is possible to run it on your personal computer. Running dada2 and R, that I can observe all the steps in between, I can change stuff, I see the output, so this is just makes so I'm just going to quickly present the general workflow of dada2 and R. So this is basically the flow chart. We of course start with our data, which is mostly in our case Illumina MiSeq paired and read files, which most of the time already demultiplexed by samples, by sample tags, of course. And yeah, then we're working. So we are going to remove our primer sequences with dada2, which is another tool, but which can be integrated into the dada2 workflow in R. I've put this into parentheses because sometimes you have multi-marker libraries and your bioinformatician or the sequencing provider has already removed those primer sequences because they were part of like demultiplexing, which also is actually the case for some of your ARMS samples. You see it in the metadata file. Some of the samples from certain sequencing runs have been demultiplexed using dada2. So the primer sequences are already removed there. And then we're just going to inspect the read quality profiles in dada2, which has like this function, which basically functions the same as FastQC, what a lot of people probably know already. And we're going to filter and trim our reads based on errors, expected errors, or on length. And we're going to cut the low quality ends of the reads. And then we let dada2 estimate error rates from, or create an error model from your data, which is needed then to actually infer the true biological sequences. And in this case, what dada2 does is it resolves differences by by one nucleotide, basically. So it creates amplicon sequence variants. So variants that maybe just differ in one single nucleotide. And this is based on the error model it has created before. And because we still have our forward and reverse reads, we are then gonna merge them. And those steps here depend on the error model estimation. And because every sequence run obviously has a different error model or like a different error characteristics, we should run those steps separately for your files from every single sequencing run. And in case you have files from different sequencing runs, you then merge them together. We're going to remove chimeras, which are PCR artifacts. And then we basically have our amplicon sequencing variants generated. And then, of course, especially with CO1 for animals, it gets a bit tricky with assigning taxonomy. You can do this in R with the database file you have gathered from somewhere, or or like you have mined your sequences from GenBank, for example. There's other classification tools which I'm using, for example, outside of R, or if you want to cluster your amplicon sequence variants first into OTUs, you can do this and then you assign taxonomy. And after this, it's basically up to you, especially for CO1, as is recommended these days to remove pseudogenes, which are mitochondrial, which is mitochondrial DNA that has been incorporated into the nuclear genome. You can do OTU clustering, you can do your diversity analysis, you can screen your ASVs for non-indigenous species, you can do phylogeography, whatever you like. Okay, so from here, I'm just going to start run the R script. Are there any questions so far? Okay, I take this as a no. Okay, so I have prepared some scripts. You guys are going to get those scripts, of course, afterwards. I have put in some very detailed descriptions for just if you want to follow this up then afterwards. And yeah, so basically, there's some links I've put in here where you can like just check out some tutorials and get some more information. There is some information here on how to best store your data in between, like certain objects in between, how to save them and so on. It says which packages you need to install before running this whole script. So yeah, I'm just, because I've installed everything, I am gonna just load the packages I need. Give me some warnings, this is all fine, we can ignore this. And I'm gonna load library ggplot2 for some plotting later. Okay, so what we're dealing with basically is I have a folder with my FASTQ files. I've just put in like one FASTQ file from an ARMS sample from Denmark and a blank file in here, the blank reads. And yeah, I'm gonna run dada2 with those. The cool thing about dada2 is that it doesn't matter if you got FASTA files or FASTQ files or gunzip FASTQ GZ files, it can deal with all of those things. So I'm just gonna tell R where my files are stored. And I have a quick look which of the files are there. So I can see it's like 4 files, 2 samples with a forward and reverse reads. And we're just gonna tell R now which of my samples, what is like the pattern for my forward and for my reverse read samples, basically. All right. Now, with the samples I've chosen here, there's still primer sequences are still in the reads, so we want to remove them. So those ones are the CO1 read, primer sequences that you guys are using for the ARMS project. So we are just going to define them. Important to notice is that the iosine nucleotide that you guys are using or that are in the ARMS manual cannot be read by UPAC, or it doesn't fit the UPAC convention, which the package here uses. So we're just going to change I's for N's, which I have done here. Okay, so we're just going to read them. And then the next function here it's just gonna create the like all different orientations of the primers, like so forward, reverse complements, and so on. So I'm just gonna run the step. Okay, all orients, and I can check. Those are the orientations for my forward primers, basically in this forward direction, complement, reverse, and reverse complement, and so on. And the same for my reverse primer. Okay. And now we want to check how often do those primers appear in our reads, in our samples. The thing is with CO1, we are basically only looking, because CO1 is longer than the fragment we are targeting, is longer than 300 base pairs. There should be no read-through into the other end of our sequences of our reads during sequencing. So we are really just looking at if we find the forward primer in its forward orientation in our forward reads, and if you find a reverse primer in its forward orientation, our reverse reads. So this is what I'm going to do here, and I'm going to create a table. So this shows us that the forward primer here appears in my forward reads in its forward direction, closely like about 22,000 times. And the reverse primer appears in my reverse reads in its forward direction, almost the same, 22,000 times. Okay, so this looks pretty good. We now actually want to remove those primer sequences, and therefore we need another tool, which is cutadapt. This, I have explained it here in detail, needs to be installed on your computer before via Python installation, for example. I've put in some links here how you can do this. There's probably going to be some problems. I had some problems too with this. It might take you 2 hours to install it, might take you half an hour to install it, because whatever system you're using, Windows or Mac, whatever, and this is just something you have to go through and check error message which appear during installation. But once you have this installed, cutadapt, we're going to tell where our cutadapt file is located for the program. And then you can actually also run those, because cutadapt's actually made as a shell, like for command line, but you can run those commands also in R. And this is what we are doing here. And we are just checking if R recognizes our cutadapt program, basically. And if it returns, okay, and here it returns the version that is installed. So R has found the path to cutadapt. So we're going to create a directory now where our cutadapted FASTQ files, for our reads, where primers have been removed or stored in. So we're going to define this here. We're going to tell our to create a directory there, and we're going to create distinctions for forward and reverse cutadapted reads. What we're doing here now is we're basically creating the command line, what you usually would do in command line with cutadapt. We are creating those commands here. So we're basically telling R that this is our forward primer we have defined before. This means that our forward primer is going to be linked. So it should be at the beginning, of course, of our forward reads. It should start, our reads should start with this forward primer. And the same for our reverse reads. So we're just going to define that those are the commands we're using. Okay. And this here is then actually running cutadapt. So we're telling basically cutadapt to remove the forward primer, the reverse primer. M equals 1 defines that we are only going to keep reads with at least the length of 1. Sometimes, for example, if you have a read there that is just made up of your primers because of primer dimers or whatever, and it removes the primer, the read basically is left with 0 base pairs length, but it's still in the file. And this is going to create some issues later. So I'm just telling cutadapt, okay, just keep reads that have at least a length of 1 base pair. And we are discard all the reads that are not going to be trimmed, where the primer sequences are not found. And this might take 30 seconds. Okay, so this is the summary. In the sample, we had 100,000 reads. We had this many reads where we had the forward primer and this many reads with the reverse primer. This is not so important. So here I have defined that we do not change the default value, the error rate of 10%. So basically, in a primer sequence that is 20 nucleotides long, we are allowing 10% of error. So if 2 out of 20 nucleotides in the primer sequence do not really match what is found in the read, it will still find it and cut it. And because our primer sequence is 26 base pairs long, and because we have defined a 10% error rate, so also primers with a length of 24 or 28 base pairs are being found. But we of course want to see is that we find primers with our exact length. 26 nucleotides has been found 98 or 97,000 times. And this just shows us that 96,000 times there was no error. We found the full sequence. 1,000 times we had like 1 error, and 74 times we had 2 errors when primer sequence with a length of 26 were found. But I've put a link here for the output. It's all detailed there again. You can look it up and then go through it again. Okay, and now we're just gonna check again if those primers actually have been removed or if they're still in our reads. All right, so nothing there anymore has been removed. This was the case for CO1 for animals. For 18S or ITS, this is a bit different because with the primers you're using for your ARMS project, there is the fragments you will get, the amplicons, will show a much higher length variability. And some of them are shorter, will be shorter than the 300 base pair reads you will generate with MiSeq. So you will most likely have in a lot of the reads a read-through into the reverse primer, meaning that even from the forward reads, you will have to remove them. So this is just an example I've put in here for 18S. I've created a folder with 18S FASTQ files, just one sample. I'm gonna tell R where this is. Okay, so this is from Spain. This is an ARMS sample from Spain for 18S. Same as before, I'm going to define, you see, like sometimes the file endings are a bit different to pattern. You just need to define this here. I'm just going to tell it that this is my forward and my reverse reads. I'm going to define the 18S primers, same as before. I'm going to create all the different primer orientations that could occur in our reads. And I'm going to check now. So this looks a bit different now. Now I don't just want to check if those primers appear at the beginning of my forward and reverse reads, but also if they appear at the end because of read-through. So we're going to get a bit of a bigger table. Okay. So what you see here is a typical output for this case. Your forward primers appear in the forward reads in their forward direction 23,000 times. So far, so good. And your forward primers appear in the reverse reads in its reverse complement orientation 19,000 times. And this the same way, just the other way around for your reverse primers. Okay, so both the forward and reverse reads primers are found in the reverse complement orientation in your reads. So we have done this. We have already defined the path to cut depth. I just put it in here for you so you can run this again for yourself later on. We are going to create this path in the 18S FASTQ directory for cut adapted files. This looks a bit different now because I also want to remove the primers in my reverse complement direction from my reads. Okay. This is the same here. It's just n equals 2 because we need to run the whole process twice now to remove those primer sequences from forward and reverse reads. So cut depth runs twice actually. This is just the only thing that has changed. All right, done already because it was only like one sample. And now you already see this is a bit different here. Because we have found different fragments now in our reads, depending on where the primer was found and where it's been cut, different sequence lengths have been removed. Okay, so far so good. So we probably see that the majority of our reads or like of our amplicons are like around 150 base pair longs for our 18S and not 300 something. And we're just quickly gonna check if those ones really have been removed, the primer sequences. Okay, most of them have been removed. There's like a few left here. This is all good. Like those ones are left because we haven't specified to remove them, but those ones here should be gone, for example, 6, 1 or 6, but it's not a big deal. Yeah, okay. And then I've told you before that some of the ARMS data sets have been demultiplexed using cut depth. And so they're already devoid of primer sequences. I will not run the next commands. I just have added them for yourself, what you can use then later on. All described here. If there's no primer sequences in your reads anymore because your bioinformatician has removed them before you're doing this analysis, then just define where your FASTQ files are. As can still happen that there's some reads with a length of 0 base pairs, which is going to create some issues later on. So just filter them to retain reads with a length of 1 base pair minimum, and then you're good to go. Okay, I'm just going to redefine my directory for the CO1 files because I'm going to continue with the CO1. All right, so now back to our CO1 workflow. We have now reads without the primer sequences. We are gonna tell R now where our forward and reverse reads are, the cut adapted reads are, and which pattern forward and reverse reads have. We are gonna check if they still match, if our forward still match to the reverse reads. This is what it prints, forward and reverse reads files match, go forth and explore. All right, now we want to visualize the quality of our reads. And the next command looks a bit complicated, but it's just, I just have defined here that if you have a directory with more than 20 files, this can be a bit, this can get a bit too much for plotting. So if I have less than 20 files, just plot it. And if I have more than 20 files, just choose 20 randomly and plot them. All right, and let's look at the forward quality plots. Okay, so this is the quality plots for the sample from Denmark, and then the blank sample. You can already see the difference, how the quality drops here for the blank samples, which of course we don't want to see like good quality reads in our blanks anyway. And it gives us the number of reads in those files. And the red line shows us that basically you see down here, this is like the cycle, so like the length of the reads, and it shows us that like 100% of our reads extend to at least like 275 base pairs, and it drops, of course, because we have removed our primer sequences. They're not 300 base pairs long anymore. I have added in the command before. I have also added a horizontal line showing us the thread quality score of 30, because what you usually want to do is we are gonna trim the lower quality ends of our reads off later on. And what people usually do is they want to keep their read quality above 30. So we should cut somewhere around here probably. All right, this is the forward reads. And then let's look at the reverse reads. You can already see that the reverse reads have a quality drop that drops a little bit earlier already, which is like usual for MiSeq, that the reverse reads show a lower quality than the forward reads. So we will most likely trim our reverse reads a bit sooner than the forward reads, around here somewhere. The green line shows the mean quality thread score of our reads at this position. And the gray stuff is a heat map basically of the quality frequency at this base position. What you can also do, I know that Christina has introduced FastQC for quality plotting of your reads even before you start the whole pipeline, and you can of course do this. For example, we could just say that we would want to plot the quality of our reads before we do cut adapt. So this is the path I have for my forward reads. I have determined before. All right. And this, what you can see already here, looks a bit different in the sense of that this red line doesn't appear anymore, because before cut adapt, all of our reads extend to a length of 300. So 100% of my reads have a read length of 300. So this is why the red line doesn't appear, of course, because we have not cut our primers yet. Okay, this is just as an example. And of course, what you can do is you can also plot a particular sample, what you're interested in. And you can define this, for example, here, sample number 1. And I have defined here, I'll give some more examples. This would plot samples 1 to 5. This would plot samples 2, 4, and 7, and so forth. And if you want to save those quality plots, you're gonna set a working directory where to save them in. And we are gonna create JPEG files for our forward and JPEG files for our reverse quality plots. And if we look here now in our folder, this is where they appear now. Forward and reverse as JPEG files. All right. So what we want to do now is we want to trim low quality ends of our reads, and we also want to filter our reads a bit. So we again have to define the pattern directory for our filtered reads, forward and reverse, which I am going to do here. Okay. A lot of explanation here. What I've just done is I've given you all the information you need for this step, filter and trim. This is the filter and trim function from dada2. We are telling it that we want to process our cut adapted reads, our files. They're going to be they're going to be processed into the filtered file directory. We are not allowing any reads which have any ambiguous base pairs. Dada2 doesn't allow this, so we set it to 0. All the explanation is found here, by the way, for all of those parameters. We are going to cut, okay, if we're going to look again at our forward reads, quality drops here. So I'm going to decide that I'm going to cut those reads, trim those reads at a length of 200, and the reverse reads at a length of 140. And bear in mind that it doesn't just trim the reeds there, it also discards all the reeds that are shorter than this length. And then we are going to define how many expected errors we are going to allow in our forward and reverse reads. And because forward and reverse reads show a different quality profile, I'm going to allow more expected errors of 4 in the reverse reads and 2 in the forward reads. And the explanation is also found here. This is how those expected errors are being calculated. So if you, for example, have a quality score of 20 at every base pair of every nucleotide of your read, then this would end up as 1%, 100, basically, this equation. And if you have a read length of 300, then you would basically have an expected errors of 3. If all of your nucleotides have a quality score of 20 at a read length of 300. So this is just how this expected error is being calculated. Trunk Q, we are gonna trunk or trim cut every read that as soon as it shows a quality score of 2, which is very low anyway, just like a safety measure. We are gonna keep reads with a minimum length of 50. You can also put this up anyway. We need longer reads. This is just also a safety measure. RM fix, sometimes in sequencing, a bacterial fixed genome is spiked in for diversity to increase sequence quality. And you sometimes don't know if your sequence provider, service provider has done this, so you can just set it as true, and it will find those genomes in your reads. Compress true and multi-thread just enables dada2 to run in parallel. This does not work on Windows, and this is why we will get a warning, but you can just set it for true, set it as true, and then nothing will happen anyway. So we will get a warning. We will get a warning here, multi-threading has been disabled for Windows, but this is just a warning. And then the output directory for our filtered reads has been created. All right, done already. We're gonna quickly check this object. Okay, so our lymph node sample came with 23,000 reads, and this many reads have survived. And you see here the quality filtering step, how it's affected the blank sample. We had this many reads and only 210 reads survived, which is what you want to see for a blank sample. You don't want like a lot of reads to survive this step in blank samples anyway. All right, I have just given a description here that, of course, what I've said before in 18S, for example, or ITS, because of the length variation, it is not clever to enforce this trunk length parameter, because this is going to discard all reads that are shorter than this. And because we have a high length variability, you would just leave this step out for 18S or ITS, for example, if the fragment you target usually shows high length variability. This explanation is given here. Okay, and then this is the first RDS command we give. We save RDS, so we're basically saving this filter and trim out object as an RDS file. And for the plotting of the quality plots before, we have defined our working directory. So we're just going to check this quickly. And this is now in the same directory here as our JPEG files for the quality plots. We are just gonna define that our sample names are basically the names of our files, everything that comes before this pattern for forward and reverse reads. And we're gonna check if those forward and reverse files still match. Files are still matching, nice, okay. Now, dada2 estimates the error profile of our reads based on the errors that appear there. Every sequencing run has a different set of error characteristics, of course. This is also why we have to run those steps here separately for every sequencing run, as mentioned before. I'm going to be really honest with you. I have read the dada2 paper quite a few times now, and I don't understand every algorithm that it has applied, but yeah, basically it creates an error rate model from our data now to be able to later on tell us which of the sequences are actually real sequences, biological sequences, or which are most likely sequencing errors. We're going to set seed because for this estimation step, we want reproducibility. This is what you do in R. You can set seed and then add any number. And whenever you want to repeat the step, you set seed again with this number, and then you will get the same results in those estimation steps. We're going to estimate the errors for forward and reverse reads. And what dada2 does, it is using by default, you can set this also. Let me check, we can just quickly learn errors. You can ask what does learn errors actually do. And gives us here that it uses 10 to the 8 bases for or nucleotides for error estimation. But because we only have 2 samples now, it doesn't reach this number of nucleotides anyway. It's using all of the bases we have, this number 4 million, in the reads from 2 samples, the one from Denmark and the blank one. And for the reverse reads, this number is lower because we have trimmed our files more strictly for the reverse read. So we have less nucleotides in our data set now, and it's going to use all of those ones in my reads for error estimation. Okay. Here's just an explanation in case that a sample has been removed after the filter and trim step. None of the reads have survived. You just need to set a few things new. Everything explained here to be able to continue with the error estimation. This is not the case here. I've just added this for your convenience whenever this should happen. And we are again going to save RDS files of our error estimation. And what you can do then is plot what has happened here. All right, doesn't look too great. Looks okay, doesn't look too great. I mean, what you basically want to do is based on the nominal equation of the errors I've shown you before. Of course, this is what you want to see, that an A nucleotide has been defined as a C and so forth. This is what's shown here. Obviously should linearly drop with your consensus quality score. What we see here is the error model, the black line that dada2 has estimated for us for all of those base pair exchanges, nucleotide exchanges. And then what we actually observe, which is the black dots. What you want to see is, of course, that the error rate, the estimated one, drops with an increase in quality score, and that our observations, those dots, fit those lines as well as possible. I have read no papers so far where people have mentioned that they did the quality plots, they have checked them out, and then they have actually gone back or changed anything. I have never read this. I think probably this is what you should do, but I think it's just no one really does it, and yeah. So yes, this was forward. Maybe Sarah, if you have done this before in dada2, and if you have observed these quality plots, those error plots, have you ever changed your pipeline in the prior steps when observing those error plots?
I've looked at the, you're absolutely right. No one actually ever reports this, but I think it's critical to at least check it out. My guess is that you've only run one sample here. So the error model is estimated much more accurately when you have the whole run, which is why I've tried to investigate your estimations if you split out a sequencing run into different projects and correct them separately. I've never found, if I have a big enough run, that I deviate too much from the expected error model. That being said, I have had deviations in runs that we've subsequently found to be very poor sequencing runs that we just had to redo entirely. So an over-clustered flow cell will have very dirty looking data that you will see in FastQC. And at that point, many users will just resequence rather than continue. So I suspect that if you have a smaller problem that's less obvious, it would show up here.
All right. Okay. Thank you.
You're welcome.
And we of course can plot the same for the reverse runs. Should look kind of the same. You can already see, like for example, at some of those quality scores here, that the estimation didn't go super well. It could be because we don't have nucleotides. We don't actually have observations of nucleotides showing this particular quality score. So yeah, this can all impair obviously error rate estimation. But as Sarah said, because I'm only doing one sample here, of course the error estimation would work a bit better with more nucleotides, which you usually have when you have more samples. But it's just like to show you how those plots look like. All right. Now we actually want dada2 to infer our amplicon sequence variants for us based on those error models, and to tell us which ones are true biological variants and which ones are most likely sequencing errors. And this is what those commands here do. This is a bit critical here, the pooling option. If you don't choose to pool, that means dada2 just looks at every library, every sample separately. This can be a problem, for example, if you have a rare sequence variant, for example, it just appears once or twice or whatever, 3 times, 4 times, 10 times in one sample, but it appears 100 or 1,000 times in another one. This will not be resolved then. In this particular sample where the sequence variant shows a very low abundance, will most likely, may be identified as a sequencing error. This is why you can choose to set pool as true, which looks at the entire data set, but this of course increases computation time and may also give you some false positives actually, and might identify some very rare sequence variants as ASVs, as true amplicon sequence variants. So pseudo is like a mix between those, and I've put a link in here where you can read about those two cases, pool and pseudo, and how this is being applied. So we now want to get our forward and reverse sequence variants. This is pretty quick. All right. So it has found this many unique sequences. We are gonna save them, and we are gonna look at the dada2 object of our first sample now. Okay, so what it just tells us here that it has found this many sequences, but those are not the real sequences actually. If we look at now the data, or like the true biological ones, it has identified. So it now tells us here that in the first sample, 133 sequences out of all of those 5,800 sequences are or have been, based on our error model, identified as true biological sequences. Okay. We still have processed our forward and reverse reads as separately so far. So we want to merge them to a single contig, and we do it with this command. Now what you can define here is when you merge forward and reverse read, how much overlap do you want as a minimum? And in this overlapping area, will you allow a mismatch of one nucleotide, for example? Do you allow 0 mismatches? I have talked to a lot of people I worked with here or checked some other papers. Usually what people do is they either keep the default of 12 and choose for CO1 or choose like a mismatch of 1 or 0, or they go with 10. So I've asked a few people who've done metabarcoding also for CO1 a few years now, and this is what they recommended. So this is what I will go with here. All right. And we can briefly look at our merges object. So we just tell them to head, like just give us the head of our merges objects for this first sample. So this sequence, this is just shows us the sequences here that are stored in there. Its abundance. This is important kind of, it shows us even though we have defined a minimum overlap of 10, obviously this one fit with 27 and Y27, because we have trimmed our reads before to 200 and 140, which gives us 340 base pairs basically. And our fragment should be 313 base pairs long, CO1 we are targeting, so we can have an overlap of 27. I am not entirely sure. I've run this whole process a few times now. I'm not entirely sure why this one here shows 28. Maybe there's something surviving that is like a nucleotide, like a read that is a nucleotide longer here. All right, and we're going to save this object. And we are going to construct a sequence table with this object. And this is just checking the dimensions of the sequence table. So 2 gives us the number of samples, and we have 2 samples, and we have 130 sequences all found, true sequence variants found in those samples. Okay, and we're going to save the sequence table. If you have read data sets of variant sequencing runs, I have defined here that you should continue here. This is only important if a sample has been kicked out of the filter and trim. Again, some explanations here, go through it whenever you run your metabarcoding data set, but this was not the case for us. What we want to create here is a tracking table so that we track the number of reads surviving in every step of this pipeline. So this is what we are doing here. We can check. Okay, this is how it looks. We have our 2 samples, number of input reads, how many survive filtering, how many survive denoising. So basically, how many of those reads made it through the sequence variant inference, and how many were merged actually. Okay, and this looks pretty good for the blank. We have a low number of reads that survive this, of course. And we're gonna write this table, and it appears here in our folder now. And if your sequencing, if your data was not generated in several sequence runs, you can just continue here all the way down to chimera removal and taxonomy assignment and so forth. I'm not going to do this now because I want to show you this, what happens if you do have data from different sequencing runs. But this is how you continue. I've given you all the information here. If you just have one single sequencing run. Okay, so the step so far is what you do separately per sequencing run, and I have done this for some other samples to get like a second one, which I'm going to use as an example now. So I have 2 runs. I have 2 sequence tables from 2 runs, and I have a second script here. Again, if you start R all over with the script, you're going to load dada2 again and define your working directory again. And we're going to read in our sequencing table of the run we have just created and the one I have pre-created before. And we're going to check what is the length distribution in my sequences there. Okay, it looks a bit not so well designed, this plot, okay, but just gives you an orientation. Of course, this is what we want to see, like a peak at 313 base pairs and 40-second sequencing run. This is a bit different, like the scale here, because we have a bit of a different distribution. Okay, we are going to merge those two sequence tables. We're going to save it, and we're going to look at the table, which shows us the length distribution in this merged sequence table. So 390 sequences of those two sequencing runs show a length of 313 base pairs. This is a good sign. This is what we want. We've been targeting this fragment from the beginning in PCR, so this is what you want to see. Okay, you can plot this as a histogram again if you want. Okay. Now in CO1 we shouldn't see large length variability. So what I'm going to allow like a variation of plus or minus 1 nucleotide in my amplicons. This is what I'm defining here. So I'm also going to keep using reads with a length of 312 and 314 base pairs. If you do other applications like metaphylogeography or something, you would probably just want to keep reads with a length of exactly 313. But we're going to be a bit lenient here. We're going to filter our sequence table to reads of this length. And we are going to remove chimeras now, which can occur as PCR artifacts, basically. And this algorithm is going to identify them and remove them. Okay, so this looks a lot now, actually. It has identified 80 chimeras, bimeras, they call them, out of 408 input sequences. This looks like a lot now, but this does not mean that the majority of your reads are chimeric. It just means that a large part of your sequences are chimeric, which is not uncommon. We are gonna save our sequence table with our non-chimeric sequences, and we're gonna now calculate how many of our reads are actually chimeric, or how many have survived. And we see that only around 2 or 1.5% of our reads were actually chimeric. So this is good, definitely. If you have 50% of chimeric reads, this would be different, for example. Okay. Now if you don't want to do clustering later on, if you want to work straight with your ASVs, you would want to assign taxonomy now at this point. And this is a bit tricky for CO1, because for dada2, no pre-arranged taxonomy file, a database file for CO1 exists. You would have to mine this from GenBank or Bolt yourself, or someone gives this file to you, which would be a FASTA file or a GunZip FASTQ file or whatever. And dada2 can deal with all of those types, and you would basically read this this file in your directory, and then you would assign taxonomy with this command. And you can save this object, and you can print a text table basically saying that this ASV is classified as this taxa. Okay. But I don't have, or I could have gotten one from someone, but I want to show you something else. I want to show you how to create a FASTA file from your ASVs and run taxonomy outside of ORDEN for CO1. For 18S, this is a bit different. I have given you a few links here with some explanations, pre-arranged database or like reference files that you can use in dada2 with this assign taxonomy command exist. I've given you the links here, and you can download those files, put it in your directory, tell dada2 this is my reference sequence file, run the taxonomy assignment command with this file, and then you will get your text table. So for 18S or even 18S, this is not so problematic. All right. Okay, so. Okay, but if this is not the case, or anyway, even if you were able to assign your taxonomy in dada2, maybe you want to create a faster file with all your sequences and with some nice like ASV headers. So this is what we're going to do here. We are going to create some sequence, some faster file from our non-chimeric sequences. And we're going to write this ASV file. Let's check. Okay, this is how it looks like. Now we have our non-chimeric ASVs as written to a faster file. And we also want to create a nice ASV count table showing us this ASV appears in this sample this many times. This is what I'm also going to create from my non-chimeric sequence table. And we are going to write this file to text too, and it should be here, ASV counts. And yeah, okay, so we have our Denmark file with a blank, and we have some other files. Apparently, okay, something has been added here, blank file, okay. So yeah, this is what we have now. This is our count table basically for our ASVs. All right, what usually dada2 doesn't really retain any singletons, so ASVs that have an abundance of just one read in your data set, but it can still happen. So what you can do then is you can run your those following steps to remove sequences that appear only once in your data set. And we're just going to read our non-chimeric sequence table in again. We're going to modify those counts in there as numeric, just give it a different modification to give the entries there as numbers actually. We're only going to keep entries with, or sequence entries with an abundance of more than one. And we're going to write a new faster file. No single. It's here now. And a new sequence count table for non-singleton ones. Okay. And now we want to track our reads through those last steps of our pipeline. So we basically counting how many reads are there in the merge after we merge our sequence tables, after chimera removal, after singleton removal, and so forth. And check it out here. Nice. Apparently there has been quite a few reads. Okay, this is after the merge step. I have to check how many actually were there in the first place. But you can see here, for example, that in our Denmark file, faster file, quite a lot of the reads have actually survived. And the same for Coster here. And I'm going to write this one. And what you can do then, this is the end of those scripts. And what you can do then is you can combine your tracking tables basically. You have this tracking table from before, from the script before. And you have this tracking table and you can just combine them in order for your samples and just put all of it together. And so that you can track the entire reads like from the beginning through the whole pipeline till the end. And usually, like I know some people who add this to their papers and supplementary materials. Sometimes the reviewers will ask for it probably. So yeah. Okay. This so far for creating the ASVs. One last step now is actually how do we get our taxonomy now with this with our faster file. I have given you two options here, one for bold, one for Midori, which is based on GenBank. This is a new tool that someone has developed. Some of you might know that it was a bit annoying before with bold that you could only upload fastest with 100 containing 100 sequences. So this German nerd has created a program which you can just download and has a graphical user interface, and you can use it from your computer. You just need to create a bold account. And then basically it takes your FASTA, automatically splits it into those 100 sequence fractions and retains a taxonomy table for all of your ASVs. Check out the link here, everything explained there, very easy. What I am showing now is how to use the web server actually of Midori. Midori is a curated version of GenBank, and they have created a web server. And that is a pretty cool tool. You could just give it a job title. Let's call it CO1 ARMS. There's different classifying algorithms which they use. I usually go with RDP, which is also what dada2 implements in its assigned taxonomy step. You would upload your FASTA now. We take the non-singleton one. You define your email address. You say that you want CO1, not one of the other markers, and then unique or longest. It basically says that as a reference, it takes the CO1 data set and based on all unique entries there, and not just the single longest entry for every species that is in there, basically. So I usually go with unique. You can define a confidence cutoff here if you want, the rest I just leave, and then you submit it. And you will get an email later with this folder, basically. And this is the output. It sends you via email. 2 files. I'm gonna extract them. Let's have a look at them. All right. This is the one that is not of interest for us. This is the one. Let's see if this worked. Okay. So this is one of those files actually giving you the important information. It gives you ASVs, and it gives you from kingdom down to species level with a confidence intervals. You can already see that some of those confidence rankings, confidence values are actually not that great, which is obviously what we would expect for CO1. Taxonomy assignment is difficult with this, and what I will do in the future, I will use this Midori one, and I will also use the Bolt Digger one, and I'm going to combine them and actually just going to keep the ones where down to the taxonomic level where both agree on the same taxonomy assignment.